Oh, well. I forgot. All right. You have to just remember those yourself. Those won't be on YouTube. All right. 1,400 pounds is the mass of the cow. You need to give the cow medicine. And the reason you start with 1,400 pounds is because you have a concentration of 5 milligrams per milliliter. Did you realize that that was a concentration unit? Did you realize that? Does it say 1 milliliter contains 5 milligrams? And is that the solution you're using? Does that make sense that that's a conversion factor that's actually a concentration? Does that make sense? It's a mass volume. You realize that now? See how it's a mass volume? It's not exactly the same mass volume we did, but is it still a mass volume concentration? Yeah. So that's a mass volume concentration unit. So you want to find out how many milliliters at the end. So is this going to be the last thing you write? Will that be the last thing? Yeah, that's going to be the last thing. But you know the mass of the cow in pounds, and it gives you a recommended dose, 0.5 milligrams per kilogram of body weight. But what do we have body weight in? Pounds. So what do we have to convert pounds to? Grams. That's right, grams and then kilograms. Or if you know the straight up go to kilograms, that's okay too. So what I'm going to do though is go pounds, 2 grams, and then grams to kilograms. And like I said, if you know it straight how to do it, that's fine. But you've got to be in kilograms. Now what do we use? What do we know? Go ahead, Ryan. What do we know, bud?
There's half a milligram per kilogram.
That's exactly right. Good job. 0.5 milligrams per 1 kilogram of body weight. So kilograms cancel. Do we now know the milligrams of drug? Do we now know the milligrams of drug that we need to use? But do we want to know milligrams? What do we want to know? What's the problem ask us for? Milliliters. So we want to know milliliters, so what do we know about milligrams and milliliters? 1 milliliter is what? 5 milligrams. 1 milliliter is 5 milligrams. Milligrams cancel, and are we now in milliliters? Does that make sense? So run your numbers. And tell me what you get. So how many significant digits do we need? 2. So what's my answer? 64 milliliters. 64 milliliters. It's exactly right. Does that make sense? Now, for those of you that know anything about livestock dewormers, and that's what this should have said, it's a pour-on dewormer. We usually say worm. I don't know why we say it that way, but we usually say I'm going to go worm the goats, or have you wormed the goats lately? Have you wormed the cattle? No, we don't want to give them worms. We want to deworm them, but we usually call it that anyway. But what's interesting is this is a pour-on dewormer. What does that mean? You pour it on their back. That's exactly right. You pour it on their back. Now, that's really interesting when you think about it, because most medicines that it seems like we take are how? Oral. But let's think about that for a minute. Are there medications that even we as humans take that are through the skin? Transdermal, I think is what that's called. Tell me something.
So we put like wounds.
Say it again?
So what you like put on wounds and stuff.
Well, in a sense, that's an antibiotic. That really is more of a barrier. It doesn't really get absorbed in the skin. What about people who smoke? What can they use? Nicotine patches. Can they use nicotine patches? And what's the nicotine do? Go through the skin. It goes through the skin. Estrogen, progesterone, there are different hormones that can be absorbed through the skin. And if you know much about medicine, and I don't, but there are actually quite a few things that are now they've discovered can be absorbed through the skin and do what they need them to do, which also goes back to me and you that are dealing with chemicals on your farm. If it can go through the cow's skin, can it go through probably our skin? And we have a problem on our farm of we forget to use gloves, and we just kind of, well, we don't have worms, do we? It's kind of a joke. Well, I'm not going to have flies, am I? But we really should be more careful. We really, really should be more careful when we use these things, because long-term exposure very likely will hurt us. And so it's something that we do need to be careful of. So, all right, let's keep going. A saline solution is used in intravenous drips for patients who cannot take oral fluids. It contains 0.92% weight volume sodium chloride in water. What does that mean? Right there, just the 0.92%. Go back in your notes on the previous page and tell me, could I use 0.92% as a conversion factor? Tell me what it means. What does this 0.92% mean? Tell me exactly what the units are, though. 0.9, it's weight volume. So that's 0.92 grams per, how many? 100 milliliters. That's what that means. It means 0.92 grams per 100 milliliters because it's weight volume, mass volume. Now, can that be a conversion factor? Yes. Do this as a conversion factor. Don't do it with algebra. Do it as a conversion factor. So now, what is your given? 250 milliliters. And that 250 milliliters is of the entire, what? Read it. Solution. And you want to know how many grams of sodium chloride, salt. So what's my next step? Say it. 100 milliliters on bottom. What goes on top? 0.92 grams. And that's it. So run your numbers. And I get 2.3 grams NaCl. Yes or no? Now, what does that really mean? Have any of you ever had a procedure done? Could be a colonoscopy. Could just be anything you had to go to the doctor or to the hospital for, and they automatically started an IV. Anybody have that happen? Anybody had an IV for any reason? If you have, so if they're using what's called normal saline, which they use what's called lactated ringers if it's just a general procedure. But there are some cases where they'll use lactated ringer solution, and then there's some cases they'll use normal saline, which is what this is. So if you were to go through an entire bag, 250, or if you were to go through not an entire bag, but 250 milliliters of that solution, how much sodium chloride are you getting? So do you think if you are a person with high blood pressure, they would use sodium chloride? Probably not. Why not? Because you don't need that extra sodium. What if you had low sodium, though? Would this be something they might use? Yeah, this would be something so again, I know this is not a nursing major class. These are things I talk about more in my nursing major class, but it's still something that you all one day will probably know somebody who's in the hospital, or you'll end up having to go get something done, and you may have this happen. And I'm only telling you this because I didn't know most of this stuff, because I didn't have to do anything in the hospital with an IV or anything I was well into my adult and I was so ignorant of so many hospital nursing things, and I've learned a lot just in teaching the chemistry class for the nursing majors. All right, parts per million. We talked about this the other day. Is parts per million pretty much the same as mass percent? Except in this case, it's straight mass or volume. As long as you have the same unit for mass and the same unit for volume, that's what you do, and it's times 1 million instead of 100. Okay? You don't have a mass volume part per million. Does that make sense? It's either mass or volume. So let's look at this problem and tell me what to do. What do we know of DDT? That's the substance we're trying to find parts per million of. So is that the solute or the solution? That's good. All right, what's the solution? 1900 grams of tissue. That's right, because we're trying to figure out what is the parts per million of DDT in the tissue. What's the problem that we have to fix to begin with? They're not the same unit. So whether you put milligrams into grams or you put grams into milligrams, it doesn't matter to me. Okay? I think I'm going to put it into grams, milligrams into grams. Do you get 0.050 grams? We have to add that extra 0 because of significant figures. It's just a significant figure issue. All right, so that grams is what again? DDT. And what is the total mass of solution? 1900 grams of tissue. Times what? No, at the end, times what? 1 million. Times 1 million. So how many significant digits?
2.
What's the answer?
26.
26 what? ppm. Just put ppm, parts per million. Just put ppm is fine. Now, I want to make a note to you on this. Make sure, and this is for many of these, but I'm going to make the note here. Make sure the solution is on the bottom and it contains both solute and solvent. In other words, do you see how this said tissue? That means the tissues of the seabird. That means everything. Up here, it said solution, so we knew it was everything. Here you knew it was the drug, which was the cydectin, but the moxidectin was the solute. Just make sure every time it's the entire solution. There may be problems, and I probably have one on here. I'm hoping I do. But I do think there's one on your homework where it will say something like this many grams of, let's just say, sugar in this many grams of water, but the whole solution would be made up of what? the sugar and the water. The sugar and the water make up the entire solution. So the mass would have to be both of those added together. So just be careful of that. That's what I'm trying to point out here. I don't have a specific problem right this minute, but that just dawned on me that I had not said that to you. So make sure you know it's the solute plus the solvent. All right, all of those that we've done up to this point are going to be what I call real world concentration scenarios, where you would have, that's going to be what's in the real world out there. These are things that you will see somewhere in life. That's how they measure concentration. Molarity is typically only used in science. Yes, medicine, but mainly science classrooms, science labs. It's easier than all these others, really, because it's always dealing with moles per liter. There's no choices. Percent composition is hard, or percentage rather, is hard because you don't know volume or mass volume. That's why it's very confusing. But molarity is always the same, but unfortunately not everybody uses molarity. So that's what we're going to learn, and then that's what we're going to use to do some stoichiometry problems in a little bit. So molarity, the formula for molarity is moles of solute per liters of solution. The symbol is a capital M, and it means moles per liter. So can that be used as a conversion factor? Yes. So this problem is straight up molarity. It says, what is the molarity of a solution of glucose prepared from 108 grams of glucose in 2 liters of solution? Now, did it say 2 liters of water? If it had said 2 liters of water, then we would have had to have figured out the mass of water. It would have been a much more complicated problem. But it says 2 liters of solution. So we have grams, we don't have moles. But we know molarity is moles per liter. What do we have to get that grams into? Moles. I give you the formula for glucose. Can you do that? Then do it. And you can't round to the end. That stinks, but you cannot round to the end. So what are you going to do? What are you looking at right now? Where are you going to find how to do this? Find the mass of glucose. How do you do that? What do you use? Periodic table. So go find the periodic table and figure this out. That look familiar? And like I said, the problem is you can't round. Do you get 0.599 yada yada? And you probably wouldn't make any difference if you did stop at the 4 because of the fact that it's 2 zeros after that. I would say it won't make a difference, but typically we say don't round, because that's not your final answer. All right, that's the number of moles. What do we divide that by? 2 what? 2 liters. So fortunately, you have that on your calculator. Just now, divide by 2. You don't have to retype it. And now, round that properly. So how do we round this? To go back to original numbers, how many should you have? 2, should be 2. 2.0. So what's my final answer? Good job. 0.30 mole per liter or 0.30 capital M. That's your answer. And you say that by saying the molarity is 0.30 molar. That's what you would say. The molarity is 0.30 molar. Yes or no? Does that make sense? All right then, let's do some more problems. We only have one more thing to do with as far as a new formula, that's dilutions, but this is all dealing with molarity. What did I tell you molarity is great as? Conversion factor. So what are we talking about right here? We're going to use it as a conversion factor? Look at that top problem. What are you given to begin with? Milliliters. What do you have? You have milliliters, and what else do you have? Molarity. What's molarity mean? Moles per liter. So is molarity going to be a conversion factor in order to get into moles? Does that make sense? Look, is this a volume? Is this a mole per volume? Yes? So what do I start with? 25 milliliters. We start with 25 milliliters. So 25 milliliters. What do we have to convert 25 milliliters to? So tell me what to do. 10 to the third milliliters in 1 liter. Good job. Milliliters cancel. Then what? Go ahead, say it, guys. Say it. What goes on top? 2.0 what? Moles per 1 liter. Liters cancel. Are we in moles? Yes or no? You know what you ought to be able to say you've learned from this class is dimensional analysis. I hope every one of you have realized that's a pretty useful tool. And yes, you are correct. It's 2 significant figures. So what is the answer?
0.050.
Very good. 0.050 moles. I liked how he put that 0 in the front. 0.050 moles, or could you have said 5.0 times 10 to the negative 2 moles? Either one. Can you do the next one? Do the next one. I won't say can you. Do the next one, and then I'll check you on it. All right, what'd you start with? 50 milliliters, good. And you converted milliliters to liters, good. And you converted liters to, what did you convert liters to? Moles, good. What does capital M mean? Mole per liter, good. So that's 0.050 moles per 1 liter. The question doesn't ask for moles, though. The question asks for grams, all right? So how many grams are in a mole? 4 aspirin. 180.17? So 180.17 grams for every 1 mole. Moles cancel, now you're in grams. So run those numbers, and what do you get? 0.45 grams. So what you get? 0.45 grams, yes or no? All right. Do the last one. Same basic setup, except it's opposite of what you just did. Do you see that? This one you had milliliters, you're looking for grams. This one you've got grams, you're looking for milliliters. So it's exactly these two are opposite. They're reverses of each other, of what you're trying to find and have. So they're the reverse. What do we start with? What are we going to convert grams to? So is it 342.34 grams in 1 mole? And now we're in moles. What can we use in the problem to get moles into a volume? Good. So this means mole per liter. So this time that's upside down. So 0.25 moles per 1 liter. Moles cancel. Am I in liters now? What do liters get converted to? Milliliters. How many milliliters in a liter? 10 to the third. So liters cancel, 10 to the third milliliters. Run your numbers. What do you get? Emma, what do you get?
14.6.
Round it to 2 significant digits. 15 milliliters. Good. 15 milliliters. Yes or no? Talk to me, guys. Question? 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 You okay? Okay. All right, dilutions. Dilutions, new, one more formula. C1V1 equals C2V2. Concentration of one times the volume of that same one equals the concentration of a second times the volume of that second. It could be molarity. It could be any concentration as long as the concentration unit is the same. Most of these will be molarity, but you still need to look at it in the terms of it could be something besides molarity, which is what it is in this problem right here. So it says dopamine is a potent drug used to increase blood pressure. How many milliliters of 4% weight volume solution is used to prepare 250 milliliters of a 0.08% solution? Well, first of all, let me just throw this out there. Do you think in a chemistry department, do you think in a hospital setting, in other words, large institutions that use a lot of solutions, do you think that we get in every possible combination of concentrations we need for everything we do? No, not at all. We make them. We make them. Every hospital, I would imagine, has its own pharmacy. I can't imagine a hospital not having a pharmacy. Hospitals should have a pharmacy. If they don't have a pharmacy, then we're talking a very small hospital, then the nurses and the doctors are the ones who have to do their own mixing. But almost every hospital is going to have its own pharmacy. We, as a chemistry department, have our people in the stock room. We get in large bottles of concentrated solutions, and then we mix them to make the appropriate concentrations. It's just like in farming, where you get a 2.5 gallon jug of glyphosate or 2,4-D. Anybody know what I'm talking about? Herbicides, weed killers. You get 2.5 gallon jugs of those. You don't go buy it ready mixed in a little spray bottle, do you, to go spread on a field? No, you get it in 2.5 gallon jugs and you dilute it, because what can you add to it to dilute it? You add the water to it to dilute it. Well, the same thing is true in a hospital setting. Or in the chemistry lab, all those the chemical reagents that you used in the dropper bottles in lab, someone prepared those. We didn't get those in that concentration. We can't give you in a chemistry lab concentrated hydrochloric acid. We can't give you those concentrated because it would hurt you. And so we have to dilute them to the lowest dilution possible that would work for you to use in that particular lab setting. So this is how we do it. This is exactly the way we do it. And so in a hospital, this is the scenario. It came as a 4% solution, but that's too concentrated to give. They have to give it in a 0.08% solution. Why do they have to give it into maybe you don't need much of it. Or maybe if you gave this, it would be such a small amount to give that it might not go where it needs to go. Or maybe if you gave it as a concentrate, it would burn like heck, and you can't give it that way, or it would taste terrible, or whatever it is. For whatever reason, it needs to be concentrated. It's the same thing with, if you think about in the real world, detergents now. And I know I say that's the problem. We don't have now and past, because you have now, you don't know past. But in the past, detergents were not as concentrated as they are now. You don't need to use much detergent when you do laundry anymore compared to what you used to have to use. Why was that? Because used to they weren't as concentrated, and basically you were shipping a lot of water. Would shipping water be expensive? When gas was $1.37 a gallon, though, big deal, right? Or 79 cents a gallon, big deal. But now gas is $3.17 a gallon. Is that a bigger deal? Yeah. So if you can weigh less and cost less to ship it, are they going to do that? Yes. So if they can ship it dry and you add the water, or if they can ship it with less water, what happens though is people still use the same amount, so then do they end up selling more? Yes, and that's why you have to pay attention. So many people use way too much detergent in their clothes, and honestly, the second time you wash them, you could probably wash them without any detergent. You're going to have plenty because you had too much in them to begin with. And I've seen that happen. Like if somebody else does laundry, and then I like just throw it in the washer to pre-rinse it, and there'll be suds all over the place because they didn't rinse it well enough because they used too much to begin with. So there's your little life lesson. Save money. Don't use as much detergent, okay? Gosh, you will learn so much. I can't believe you're only going to remember nomenclature of all the things I've taught you, but I'm glad you're going to know nomenclature. All right, so dopamine. So tell me what to do here. You've already got the problem done. I've been yapping and you've got the problem done. Tell me what to do. What are we using? What are you looking for exactly? Tell me, Lucas. Say it again. Volume 1. Are you looking for volume 1? Good job, buddy. All right, so C1. What's C1? What did you put for C1 V1 equals C2 V2? What did you put for C1? 4%? All right, we don't know V1. What did you put for C2?
0.080%.
Good. And V2?
250 milliliters.
Very good. Now, the units are going to cancel out. You'll end up with a milliliter unit that's not canceled out. So, do your math. Plug and chug. You do not need to take them out of percentages because the percentages cancel. Don't take them out. So what's your final answer?
5 milliliters.
How do we write that significant figure-wise?
5.0.
Very good. And again, could you plug it back in to make sure you had the right answer? Do the next one. There's some things you have to do here that are a little different. What's something you have to do at the beginning? Good. You got to give them the same unit. Got to give them the same unit. Let me ask you a question. Is this actually a dilution problem like we did it? Yes or no? No. It's not. This is not a dilution problem. This is not a, so from the rest of these, they are and they aren't. Some of them are, some of them aren't. But this is not a dilution problem, and that's part of the reason I threw it in there. Because you've got to be, you've done all these different problems. You've got to be able to decide, what do I do here? What do I do? That's what life is about. What do I do? And this problem, that's what you have to figure out. What do I do? What do you know in this problem? And what word don't you know? Some of you don't know a word. What word do you not know? 2 words then maybe. Tell me. There you go. There's one you didn't know. What was it? That's not the word I was thinking. What did you say though? You're right. Sterile? Sterile means what? Clean, perfectly clean, perfect water. Vial. What's a vial? Small container. A small container. A vial is a very small container. Now, I'm surprised you haven't said the other word. I figured you don't know. You can't say it. Is that the problem? Reconstitute. 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 What does reconstitute mean? Put liquid in it. Bring it back together. Put liquid in it. So let's read this. A 2.5 gram vial, in other words, a little bottle that contains 2.5 grams of the diuryl, says to reconstitute, mix with 20 milliliters of water. So you're going to add 20 milliliters of water to that vial. This is something people do. If you ever pay attention to, and sometimes they don't do it where you are, but there are times when your nurse, when you're getting ready to have a shot, will have two vials, and one vial will be a powder and the other vial will be a liquid. And it's water and the powder, and they will put the syringe with the needle into the vial of water, draw it up, squirt it into the vial that contains the powder, then draw it up, swirl it, shake it a little bit, then draw it up and give it to you. That is reconstituting. Now, again, what have we just talked about? Why do they do that? What are some reasons for doing that? Shipping and longevity. A live vaccine, a live virus vaccine that has to be kept alive, they do not wet it. Once it's wet, it has to be used so fast. All of the different COVID vaccines that when they were coming out with them left and right, and all of that time, those were sent out in a powder form that you had to reconstitute with water. Because it's a live, and most of your vaccinations are going to be like that because they're live. Many of them are live vaccines that have to be reconstituted before they're given because they are more stable when they're not wet. When things get wet, that's when they become less stable. Okay, now let's look. It says you've got a 2.5 gram vial of diuryl with 20 milliliters of water. Is that a conversion factor? Are there going to be 2.5 grams of diuryl in that 20 milliliters of water? Yes. Now, do you have to actually figure out the mass percentage or volume, mass volume? No, that's a conversion factor. So use it as a conversion factor. You have been prescribed 500 milliliters or 500 milligrams of diuryl. So the question is, how many milliliters of that solution will you need? So what do you start with? 500 grams, or milligrams rather, 500 milligrams. You start with 500 milligrams because that's how much of the drug you need. You just need to know how many milliliters of that particular reconstituted solution do you need to take. So what do? Milligrams to what? Grams? So 10 to the third milligrams, 1 gram. Milligrams cancel. Grams to what? What do you know? Let me make some notes. This is diuryl. This is now grams of diuryl. You want to know what? Milliliters of the actual solution. What is the actual solution? How do you make the solution? 2.5 grams of diuryl to make a total of what? 20 milliliters of solution. I didn't mean to mark off. Does that make sense? So what do you get? 4. 4.0 milliliters is the final answer because you have to have two. And that's okay if you got it a totally different way. That's okay. That's okay. That's okay. If you got the right answer, but you did it a different way and it makes sense to you, then that's fine. Okay? I'm a dimensional analysis lady. I like doing it that way. If you can get it a different way, I'm okay with that too at this point. You've learned dimensional analysis. You're going to need to use it sometimes, but I'm okay with it. Can you do the next one? Can you tell me, the next one has a dilution portion and it has something else. Tell me what to do. You got your head nodding over there. Tell me what to do. What's the first thing you're going to do?
So it gives you the dose of 3.375.
Correct?
So that's your given.
That's going to be a given for a dimensional analysis problem, but you don't start there yet. Why not? Because this is the given wanting to know how much of the, look at that word, diluted solution. It's not diluted to begin with, though, when we start the problem, is it? No. So what do we have to do? With this, correct? In other words, do we do a C1V1 equals C2V2 problem? Yes or no? Yes. We have to do a C1 V1 equals C2, we don't know, V2. 5 milliliters is V2. So do that dilution problem first. No, do C1V1 equals C2V2 first. So what is that new concentration? (21.2 milliliter or 22.2 milligrams per milliliter? Is that what you get? So C2, in other words, the diluted solution is 21.2 milligrams per milliliter. Yes or no? Sorry, I'm not writing or holding it where you can read it. Yes or no? So now it says how much of the diluted solution, this is the diluted solution, do I need to give? If I need 3.375 grams. So now where do we start? Now tell me where to start now. 3.375 grams. I'm going to be using the diluted solution, not the concentrated solution, to give it. Why? Because it might burn too much if you give it as a concentrated solution. It may go in too fast. It may react with your skin. Who knows? We just need to give it as a diluted solution. So what do we convert grams to? How many significant digits do we need to use? How many? 2. Only 2 because of 5.0 and 2.0. So final answer is what? 1. Good job. 160 milliliters without a decimal. 160 milliliters without a decimal. Guys, I'm going to tell you, I'm going to put a star on this because I'm going to tell you something. There is a problem like this on your homework. There is a problem. I'm 99% sure there is a problem like this on your homework. You are going to see a problem like this again. You are at the end of the semester. You have got to know how to do a multi-part problem. This is a similar problem to what you are going to see in the future. So when you find a problem like this, this is it. This is how you do it. Pay attention, okay? All right, I'm going to let you do these later because these two are just like see top of page. These two are just like the top of the page. I put them on here again to get us ready to do what we need to do next, but I'm going to go ahead and show you how to do the next. I'm going to go back up to the top though. I am going to go ahead and have class on Thursday because we have more practice to do, and I honestly think most of you need it. Okay, I think you need to come. I'm not taking attendance anymore, but I do think you need probably the extra practice, okay? I mean, any class is your discretion. Obviously, people don't show up to class, so it's your choice if you come or not. I'm not going to penalize you one way or the other or benefit you, but it'll benefit you. I don't think it's not going to hurt you if you don't come, but I do think it would be helpful for you. You do these later. Now, I'm going to show you something at the top, and then I want to do a couple of problems, and then we're going to go. So if you look at the top up here, I told you that you're going to use molarity as a conversion factor in stoichiometry problems later, which is what we're getting to. If you have volume and molarity, what are you able to find? Moles. Is that important in a stoichiometry problem? Does that make sense? So now let's go back to one more thing that I've said today. Do most reactions happen when they're dry or when they're wet? When do things happen? When do reactions take place typically? When things are wet or dry? Wet. That's when the reactions take place. Think about cooking. I made cookies this weekend with the boys, and almost every recipe for cookies or brownies or cakes, you mix your dry ingredients all together, then you add your liquid ingredients. If you put those dry ingredients and just left them, anything gonna happen? No. When do things start happening? When you add your liquid ingredients. That's when they happen. And that's why typically you add them, you mix everything up first, then put them together because you need that reaction to happen right before you put it in the oven. And so that's chemistry. Up until this point, we've been doing stoichiometry with dry. That's what we've been doing. But think about what you did in lab. Did you just use dry things in lab? Pretty much everything you did was putting maybe a dry thing in a solution or maybe two solutions together, but did you ever in lab put two dry things together and this reaction occur? No. So hopefully you realize that's why we have to learn how to do solution stoichiometry. So this first one talks about, and I'm really trying to help you on how I wrote it here, use the equation. I have given you a balanced equation. That's how you know that it's stoichiometry. Use the equation, and it says you want to find number of moles of aluminum hydroxide, but you have milliliters and you have molarity. What can you get from this information? Of who? BaOH2. Does that make sense? And then you can do a mole to mole ratio to get moles of aluminum hydroxide. Yes? So do it. What are you going to start with? What's the first thing you're going to start with? There you go. Don't forget to put who you are. So 500 milliliters, that's BaOH2. What's our conversion factor to get us into moles of BaOH2?
5.75 moles.
Good job. 5.75 moles of BaOH2 over 1 liter, because molarity is moles per liter. Once you are in moles of BaOH2, what are you ready for? Mole to mole ratio. And that's the same you were doing before. So you go to your balanced equation, and what goes on bottom? 3 moles of BaOH2. And what goes on top? 2 moles of AlOH3. Is that what you wanted to be in? Does that make sense? So run your numbers. What do you get for your final answer? 1.92 moles, and that is proper significant figures. 1.92 moles of AlOH3. Yes or no? Okay. I want to leave this one for a minute, and I want to talk about these two, because I'm going to give you something for these two that you should already be able to do, but I want to give it to you so that you could practice on these. What's not given in those two problems? The whole page is solution stoichiometry. What is not given in these two problems? A balanced equation. And you have to have it. Now, part of your test is comprehensive, meaning full semester's worth of stuff. Okay? So your final exam is a number 4 test, which is gas laws and solutions. That's your 4th exam. That's 100 points. That's your 4th exam. But there is a portion of your test that's over test 1, 2, and 3. Test 3 had on it being able to balance an equation from words and predicting products. That's what these two are. What are our reactants in this problem? Let's call this 1, 2, 3, 4. What are the reactants in number 3? NaOH plus H2SO4. Now, what kind of reaction is that? Double displacement. What's going to be formed? Sodium sulfate, very good. Na is a what charge? +1. Sulfate is what charge? -2. So how many NAs do I need? 2. SO4 plus, what's left over? HOH. Water. HOH. Write it as HOH for yourself. But on achieve, what do you write it as? Good job. Make sure you do that. Now, is that balanced? I don't know. Haven't balanced it. I don't think it is balanced, so you better balance it. Come on, guys. This is not hard to balance. Come on. First thing you did is what'd you put over here on Na? 2. That made 2 OHs. What'd you put over here? 2. That made 2 H's. Do you already have them? Boom, you're done. Don't make this part hard. Okay? All right. You all try to write the balanced equation for this one, and you're going to have to probably look up acetic acid if you don't remember how to do that, but that's good practice. I need to make a phone call, so go ahead.
34 H's on the left side.
this H2SO4.
2 plus 2 is 4.
Oh, okay, sorry.
So 2 plus the,
Yeah.
let me tell you what I'm doing though. I'm not breaking down my, I'm treating it as 2 NAs, 2 NAs, 2 OHs, 2 OHs, 2 H's, 2 H's, and then SO4, SO4.
Gotcha.
Okay? All right, I'm going to stop here for right now. We're going to come back on Thursday and finish up everything. And then I also, guys, you need to study for your final, and it's your time Thursday to ask me questions, okay? And I'll post this video later today.